Hi, everybody. Welcome to Everyday Metallurgy. This episode is something I doubt you have ever heard of before. Normally, we talk about 3D printing, but today we're taking it one step further. We're going into 4D printing. If you know what it is, well, you are one of the first movers. If you don't know what it is, I think you should stay here for the next about 24 minutes. Then for sure you will learn what 4D printing is, because this is advanced material technology. Enjoy the show. Hi, Mehrshad.
Hi, Peter.
Welcome to the podcast Everyday Metallurgy.
Thank you. Thank you for having me.
Today we are going to talk about some very special materials, shape memory metals or shape memory materials, because it's not only metals, it's in fact also polymers that can be shape memory formed. Can you give a little background about yourself, where you are, and what you work on?
Yeah, sure. I'm Mehrshad Mehrpouya. I am assistant professor at the University of Twente, the east of the Netherlands. I'm a part of department working on design, production, and management, and a specific research group that we have we are working on advanced manufacturing. So mainly what we do, as the name states, is on advanced manufacturing, but most of the projects nowadays we are doing with the main focus on additive manufacturing processes.
Yeah. Moshe, I read your book.
Yeah.
And it was so inspiring. So if you have it nearby, can you show it? Because I would love to share it with people. I learned so much about this that I needed to talk to you.
Yeah.
Yeah. But first, can you give an introduction to what is a shape memory material?
Yeah, definitely. There are different type of smart materials already in the literature and also different research group working on that. And one group nowadays, at least in last 2 decades, is quite famous and common are shape memory materials. So we know shape memory materials mainly with shape memory alloys or shape memory polymers, but there are also the other type of shape memory materials that, for example, we know the type of shape memory gels or shape memory ceramics. In general, shape memory materials are a group of the material that have capability to return or revert to their original shape after a kind of deformation. Yeah. And this shape recovery that we call it can happen based on uh, mainly a specific external stimuli. It could be like temperature, could be, for example, magnet field, could be even chemical reaction like pH or moisture, light, and different things. So this group of materials, as I mentioned, that we call it as a smart material, can have a different application and also the different way we manufacture them, produce a different product. So what we are trying to do to try to understand the material well in the first step, and second, to understand how to make a new product based on that and use it for the different applications.
Yeah. So if we dig into the history of it, I really like the way I heard it was found was by an accident. Can you disclose how it was discovered?
Yeah, definitely. Um, Maybe the most famous story is about the shape memory alloys. It was a Swedish, let's say, scientist, Arne Olander, in 1932. He discovered in his lab a specific behavior of the material, and then he called it shape memory behavior, and it was for a gold cadmium alloys or composite. And 1932 seems was very early to discover such a material because 30
Mm.
years later, another scientist or researcher in naval laboratory in US, his name was William Bowler. He discovered nickel titanium as
Mm.
a shape memory material, and this is one of the most famous of the shape memory materials so far, and
Yeah.
lots of applications in the different industry. And then from that time, 1962, and onward, the application of this material become more common. But we know most of the products after 2000 in 20.
Mm.
Uh, and nickel titanium, maybe a little bit more information about that. We know it as also NiTi and also NiTiNOL, the other name.
Yeah.
Uh, Lots of application about that is for medical specifically and aerospace applications.
Mm.
And nowadays we discuss about how to manufacture them, and this is the field I'm working on that.
Yeah. Yeah. I think the NiTiNOL name was nickel titanium, and the NOL was the letters for the place it was discovered.
This is new to me, but the DT as I know, is nickel titanium. So if
Yeah.
node is something additional, I hear from you.
Yeah. Hey, I'm just disturbing because I have digged a little deeper into the nitinol material. It was invented or found in 1959 at a naval research center in US. In fact, the material was meant for the cone of a missile because it was developed, or the purpose was to develop a material that could take the heat from the re-entry in the atmosphere from the missile. But more or less by accident, the metallurgist working on it found that this material had different phases depending on what temperature was. But first, 2 years later, in '61, they found what it really was. So the ability to work as a memory metal was not found day one, but it took, in fact, 2 years to find out that. So back to the show. And I think it was meant to be discovered as a high temperature material. So
Yeah,
they made trials on high temperature applications. It failed, but
yeah,
suddenly this new thing appeared that it could return to its original shape after bending it.
true. That is
Mm.
correct. And uh, we have a different type of research about the shape memory alloys and even about nitinol or NiTi family. So some group of the researchers working on developing a new type of alloys with different functionality. For example, if you add additional elements to that, increase their temperature or decrease it. So this is
Mm.
one thing people work on that. And some people try to understand how to manufacture them instead of conventional manufacturing with additive manufacturing, the field I'm working in.
Hmm.
There are also some people try to use the material as it is for the design of the smart product or features, and this is also some another group of the people. So sometimes all these three fields, let's say, work together for a specific purpose to,
Mm.
for example, as a project to make a specific smart product in the end of the day, and that is the interesting field indeed.
Mm. Yeah. Uh, but now let's dig a bit deeper into the technical issues, because
So
when reading about it, it's so difficult to understand why it works. So
yeah,
can you describe what is happening inside the material? There's magnetic formation, then, but it's going up and down hysteresis. Can you help me understand better what is happening inside
definitely.
the material?
Sure. For shape memory alloys, when we are talking about shape changing or shape recovery, we are talking about a specific temperature. That temperature is transformation temperature. So mainly what happening is, let's say the changing the material phase from cooler temperature that we call it martensite to higher temperature that we call it austenite. So changing the temperature or the phase of the material, change the macrostructure of the material, and based on that we have, let's call it that magic behavior of the shape memory materials. I can share a picture with you, and maybe that would help to understand it better.
Yeah, that could be nice.
Yeah,
It,
sure.
yeah, it's very abstract just to imagine what is happening.
Yeah, so what you see here, actually, this is a typical stress strain diagram that we usually have in all materials, but here that you see another axis, that one is
Mm.
temperature. So I want to go through the whole diagram and give this explanation because when
Yeah.
we are talking about the shape memory alloys, we're mainly talking about two different type of shape memory alloys. A part of them, we call them superelastic material. The other part, we call them shape memory effect. So again, I back to the explanation I had, and that
Mm.
one is related to the transformation temperature. So the first one that you see here, and I have a red dot on the picture,
Yeah.
is the stress strain diagram. And I want to show you A, B, and C. So
Mm.
what we do, simply we apply a load on the material. And when we apply a load on the material, what happened exactly? Yeah, this is a super elasticity. Let me just show you this. And I need to use also my marker to make it easier to understand.
Yeah.
So what happened here exactly is when I apply a load on the material and when I remove the load, the material can come back to the original shape. So
Mm.
why? And this is because the material is already activated and the material in the austenite phase. And what is
Mm.
happening in the superelasticity is exactly the moment that we apply a force in the state the material is activated and is above the transformation temperature. However, if I choose another type of material or I apply the load in the temperature below the transformation temperature, the
Mm.
second situation would happen. And the second situation is shape memory effect.
Yeah.
When I apply apply the load on the material like C, D, and E, like you see, and apply a force on that.
Mm.
However, I still have, let's say, the deformation and the strain here in this area. To be able to bring the material back or return it to the original shape, and then I need to apply a heat on the material. And for applying the heat on the material, I heat it up to the
Mm.
specific temperature, and it is normally above the transformation temperature. And then after that, the material can get the original shape and come back to 0 point. So
Yeah.
if I want to give you a good understanding of that, just follow the red point I'm already showing you here in
Mm.
this diagram.
Yeah.
Uh, Two good example of these two superelastic and shape memory effect material. The first one is a superelastic material. So what you see in the hand of this person is
Mm.
superelastic NiTi wire. As I
Yeah.
mentioned, is already activated. As soon
Yeah.
as you remove the load from that, it come back to original shape. So it is exactly this area, orange area I already mentioned.
Mm.
And then the second type of the material, you apply load on that, like this spring was deformed completely. So I'm talking about the green area here. And then
Yeah.
you increase the temperature, like
Mm.
here is heating on top of this stove, and then material can recover this original shape. So there are mainly two type of shape memory alloys that we are
Mm.
using nowadays. Yeah.
Yeah. Yeah. It's pretty amazing. Uh, when you talk super elasticity, what strain level are we at? Because most material have certain level of elasticity, but how much do you need before you can call it super elastic?
The level of strain that we are talking about is 7 to 9% of that. However, these 7 or 9% could be also related to different things. How you manufacture the materials, what is the composition of your materials,
Mm.
and let's say what is the state of the material and the shape and geometry of your material. So sometimes in the design process, we can play or tune with this strain rate. For example, imagine if you, instead of using a bulk material, like for example, this pen in
Mm.
my hand,
Yeah,
use like a lattice structure in a specific shape and you can deform it more.
yeah,
So somehow we can tune this strain and functional behavior of the material. Yeah,
yeah. So it's not only the material, it's also design of the component on macro scale.
that is correct. For example, if I want to give you a real example following I showed you earlier, it's not new to use NiTi or shape memory alloys for stents, for example, cardiovascular stents.
Mm.
So it's been a long time there are shape memory, let's say, a stent in the shape of like a tube shape. And uh, the way they make it uh, is combination of conventional manufacturing and newer methods. So let's say through the conventional manufacturing, they make the tube shape of NiTi, let's say
Mhm.
NiTi tube. And in the next step, they use like laser cutting to make a specific shape of that, like a spring shape. And
So
based
they,
on
they
that,
cut out material.
that's true. And based on that, they can make it very flexible and move it to any direction they want.
Mm.
So the
Mm.
structure, architected structure can help you to make or achieve a specific deformation you are looking
Mm. So the typical manufacturing methods is it melting, casting, and then you can roll it and make plates and sheets, or are there other methods for manufacturing?
for. Yeah, you're right. Let's say the main manufacturing process is still conventional. So lots of products already available in the markets, like in the shape of wires or tubes or let's
Mm.
say strip or plates. Yeah, but what the recent research, not even recent, let's say in the last decades or 15 years, people from the different groups and from different universities and also not universities, research
Mm.
institutes, try to substitute that with the other type of manufacturing process. For example, when I'm talking about additive manufacturing and the whole philosophy of writing the book I showed you
Mm.
earlier is exactly
Yeah.
about that. Because what the researchers are trying to do, trying to find a new way to make a complex structures. Because thanks to additive manufacturing, we can have it and we can make complex structure from different
Mm.
materials. Let's call it from polymers to metals or ceramics,
Mm.
hydrogels. So the idea was how we can use additive manufacturing processes specifically for shape memory materials. That doesn't matter, shape memory polymer or shape memory alloys. There are different type of
Mm.
manufacturing and 3D printing. You can use it. And that's why the initial idea of this book was, okay, if we can add or gather all this information from a different researcher all around the world
Mm.
and have it documented in just one unique book. And then we did it. So this book, of course, there are two editors, myself and also my colleague, Professor Alahimia, but each of these chapters is written with very famous, let's say, researchers or research group. They
Mm.
work specifically that topic. So we have a researcher working on material development and discuss that in the book to, let's say, different type of manufacturing process. Because when we are
Mm.
talking about additive manufacturing, it's like powder-based, wire-based,
Yeah.
DD,
Mm.
LPBF, and there are many, many. Yeah.
Yeah. and we have to remember my heart is in powder metallurgy. So
Oh, okay.
yeah, yeah, yeah. So that's also important to mention that they can be shaped with powder metallurgy roots.
Yeah, that is correct. Actually, one of the main, let's say, additive manufacturing process is LPBF or totally PBF process, and that is PBF stands for powder bed fusion.
Yeah.
So we still have powder there, and we need
Mm.
the powder, and there are lots of businesses working on how to make high quality powder for different type of shape memory materials, but
Yeah.
still NiTi is a dominant material in the market and in
Yeah. Absolutely.
most of application of the shape memory alloys.
Yeah. Mershed, there was one thing in the book that amazed me most.
Mhm.
It was a new term. I've never heard it before. It's called 4D printing.
Yeah,
I People have been talking about 3D printing for decade now.
well,
So when I read this 4D printing, it was like, what is that? That is not possible. So can you explain what it is? What is going on in 4D printing?
yes, definitely. Let's say 4D printing, if I put it in very simple way, is let's say integration of smart materials and additive manufacturing technologies. So the 3D printing technology exists already. If we print smart materials with that, then we can have a different, let's say, shape of the material after the 3D printing, because these smart material in response to external stimuli, they can change their shape. So these 4D or fourth dimension, exactly because of that, because due to or the response to the external stimuli, they can change their shape or properties over the time. And that's why instead of 3D printing of, for example, shape memory materials, they call it 4D printing. But I should be honest and say there are also some researchers, they do not like to use 4D printing for that. And they said they are
Mhm.
still 3D printing, but a smart material. But they
Yeah.
do not have any problem. So we can use both of them. 3D printing of the smart materials or 4D printing. Both of them are fine.
Mhm. Yeah. And do you have some examples on how you can change
Yeah.
the properties or add this the time scale to a component and the function of it?
Yeah, definitely. I have one simple example of for that. And this example is for this time for shape memory polymers because of my research, I work on both of shape memory alloys and shape memory polymers, although they have two different words, and sometimes the researchers working on one, they do not necessarily work on the other because we know the materials are totally different. But for me, it's really interesting to learn from both of them, and every day in the different research, I learn
Mm.
from that. So what I'm sharing with you right now is, let's say, a printed logo of the University of Twente, the university I'm working for. So this is,
Mhm.
um, let's say, a shape memory polymers. If I want to be very specific, a combination of PLA and PPS biopolymer.
Mhm.
Like what you see in the first picture is completely rigid material and printed like a normal other 3D printed parts.
Yeah.
So the point is you can deform these structures. I can give you more explanation how you can deform it because like shape memory alloys that we have transformation temperature, in
Mm.
shape memory polymer that we have a specific temperature that we call it TG or glass temperature. And above that temperature, material can be activated. So the point is, if you heat up the material above that temperature, for example, here in this case, the
Mm.
TG is something about 60 degree, and we could heat up the material like 65 or something, deform the material. And if you cool it down, and then the material get the new shape. So the new shape that we see here is a deformed shape.
Yeah.
However, if you heat up the material again, above that temperature, the material can return to the original shape. So the video I show you here is the shape recovery of the deformed logo. And here, what you see is happening in hot water. In
Yeah.
hot water means above that temperature, and then the logo can come back to original shape. So this is, uh, let's say, a very typical and common example of the 4D printed part, how you can recover the original shape. And also same thing can happen also for shape memory alloys, specifically super elastic materials. So there are some examples
Mm,
and also published in the previous work that you can deform the material, heat it up, it come back to original shape.
mm. Yeah, that was the story about the theory behind this 4D printing and the shape memory materials. In the next episode, we'll take a deeper dive into what is the real purpose of everyday metallurgy. It is to talk about everyday applications. So come back in next episode. We'll go into real life.